Students. This is going to be a video where we look at Euler's method, and then I think I've posted a couple more examples from random people on the internet, like one from MIT, for additional, just a couple additional problems. But we'll go through one together first. So first, I wanted to explain the theory of Euler's method. I couldn't find anything like that on the internet, so I think we need to talk about it together. So what Euler's method is it's basically a numerical approach for finding solutions to differential equations, but not like just any old solution, but a particular solution. So this is like for an initial value problem or something with an initial condition. So by now, if you're in since you're in Calc 2, you should have a pretty fair idea of what an initial condition is. It's just a point that you kind of drop in the flow of the slope field, which represents the family or the general solution, and lets you pick out just one. So this is a numerical way to do that. It's pretty much the most basic numerical method, but it's built into a lot of computer programs, and it's how they do a lot of basic things in terms of solving differential equations. Very, very common. So good, definitely a really important method to have a grasp on. Anyway, so let's say we have a differential equation and it's expressible in a format where you just have the first derivative equals some function of x and y. So it's got to be in that kind of form, or you have to solve it to be in that kind of form first. So if you're going to build a computer program around this, you need to make sure it solves like that first. Okay, and I think this picture over here is really informative. So let's say we have some initial condition, and that is that we have some point that this solution has to pass through, so x0, y0. And we can now go ahead and compute the slope at that point, and that kind of gives us a starting point in our approximation. So here's the idea. I think the picture over here is really good. That's the main reason I used this, because it has a really nice picture. So you can see that the actual exact solution to the differential equation, we're going to come up with it by separating variables, or first order linear, or some other method you haven't heard of yet. There's the exact solution out there. You can kind of think of that as being in God's brain. Maybe we don't know how we'll get it, so we're trying to use Euler's method to come up with an approximation. So here's how Euler's method works. First, you start at the initial condition, and then you move one step at a time from that initial condition. Now the way you're going to do that is you're going to use kind of a shooting method based on the slope. So to get from the first point right here, put it in red there, you see, to the second point, which is up here, which is, notice, not exactly on the solution. We're just going to get better and better as we go forward. But it's not going to be perfect. It's just an approximation. It's a numerical approximation. That's what numerical methods do. Sometimes they'll converge to the real solution. That's what we hope. But anyway, and then we're going to go one more step out to the next spot. And you can see that after each step, the Euler approximation kind of tries to hug the curve and get in closer and closer. So how does that work exactly? So to get from the first initial condition out to the next step, we go from x0 to x1. So I think that you can clearly see you have to pick some step size, and this is what you have to pick or what the problem hands you. So if they say make the step size a certain amount, you say, okay, I'll make h a certain amount, and then you go off from your initial x value. And then to get the y value, you say, okay, I'll go off from my initial y value, and I'll go off this much. You can see in the picture here, this is really obvious. You just step forward that much in terms of x. Very easy. But how do we get this, this part right here that I've done in green? For that, I think that it might help to go back and review linear approximations. So let's go back and look at a picture of that. So if you remember in the first year of calculus, we talked about linear approximation. And we used this linear approximation, which is another shooting method. So Euler's method is basically just doing linear approximation lots of times. That's all it really is. So let's go back and think about linear approximation with this picture. So we had a first spot right here, and we constructed a tangent line. I guess I'll make it blue since theirs is blue, at C. You see that? So we constructed a tangent line at this spot, which they've called C. So if we do that, we take the derivative of C, and then we go, okay, remember we go like y minus y1 equals m and x minus x1, except we just do that with where they've picked it here. So they said let x equal c, so you say, oh, okay, there's x minus c right there, because x1 is the point c. And then that means that y1 must be the y value that comes with c, so f of c. So you can see that over here. So you see what they did is they called this f of c, and then they just added f of c on both sides. So I guess I could have done that down below. Let's do that down below. So if you call that y, and then y1 is just the y value corresponding to the x value we've put in, which is f of c, and then m, if you remember, we just say is the slope at that point, so that's f prime of that point, which we called c, and then over here we had x minus c. Then you just add this to the other side, and you get y equals this thing exactly right here. Okay? So then, when we were doing linear approximation, we interpreted that, right? We said, well, let's just say that the next y value, in other words, let me clean up this picture, the next y value that we're trying to approximate, this guy out here, is going to be the launch pad y value, which is right here, right? And then plus or minus, depending on which way you're going, but we're going out to the right, so it'll be plus the derivative, the tangent line tells you like a direction to shoot in, a nice direction, and this tells you how far to shoot, right? This x minus c, which we now call delta x. So that's why to get from this initial y point, which in the Euler's method is going to be called y0, you have the y1 in Euler's method is going to be that initial y coordinate, which is like y0, plus this much out, plus this much up, excuse me. This is how far up you're going to go. So don't make this harder than it is. It's really simple. It's just thinking about a tangent line and rearranging the tangent line so that you get a launch pad, f of c, and another little bit of y value, which is this thing. It's just a new way to think about it. So in our new Euler notation, we're going to have that the new y value is the old y value plus, this is going to be a little bit more height, plus some height, which we're going to say this part is h, and this part is like f of x0, y0, our initial condition, where capital F is like a derivative, okay, multiplied by h, which instead of calling it delta x, now we're calling it h. So this is really something you've seen before, and then we're just going to iterate, and what iterate means is we're going to do it over and over again. So can you see that down here? So after getting to the second spot, we're going to try to continue building our approximation, because it's not just 2 points, it's an entire curve of points. So then we're going to go to the next spot by taking that previous spot plus another interval h. So we're going to keep this next spot like the same amount h. So this is h, and this is h. Okay, and each time we're going to feed in the previous place we got to. So now we're going to feed in this y1, and then we're going to shoot forward based on it. And then the next y3 is going to be y2, and then we're going to shoot forward based on where y2 was. And hopefully we're going to get closer and closer and closer to that curve. So y3 hopefully would be something like this up here. And this is y2, and this is y1, and this is our initial condition y. Okay? So that's how Euler's method works. It's just iterating basically linear approximation. And you can program a computer to do it really simply. We might do that in your class depending on which year this is. I don't know. Okay, let's do one example. So this one says we have a differential equation. Looks like it's in the right form. It's y prime equals some function of x and y. They give us an initial condition, and they tell us the step size. So you might, in the real world, have to pick your own step size based on how good you want your approximation to be. Obviously, smaller steps are going to produce a better approximation. If we go back up to the curve here, oops, here, we erase some of this junk. You can clearly see if we picked smaller steps, instead of steps that were like this big, what if we picked a step that was like this big? Then that would probably be like right there, and you can see that it's already closer. And then if we went out that much more, then we'd use this guy and probably get to about right there. And then if we went out that much more, we'd use this guy and probably get right there. And you could see that that approximation would probably hug it better because the step size was smaller. Alrighty? Okay, so let's do it with this one. They've got a pretty small step size, 0.1 relatively. Anyway, so we're just going to follow the algorithm and compute new y values as we go. So first we're going to start with the initial condition y value and shoot forward from it with that step size. So we're going to go, the initial y value from the condition was 1 plus the step size, and then this guy. How do we get this guy? Oh yeah, don't we just go x minus y, because that is the value of the derivative. So if we go back here and look one more time, sorry to bring you back and forth, but that's f prime because f prime has that new notation. Yeah? F prime is like y prime, which now we're going to call f of some x and some y. It might not have both x and y in it, but ours does. So that's why we've got to go x0, y0, and that's how you get this one. So now this is y1. So now y1 is now going to get fed back into the algorithm. So then it's going to start from there and go from there. And it's going to say, okay, 0.9 plus the step size. And then it's going to say, okay, the new x value is going to be x plus h. So we go out 0.1, so 0.1. And then we're going to put this in there too. And then we get this guy. So this guy's y2. So then y2 gets fed in right here. We launch from there, and then we go plus the step size, and then we go another h forward, one more step forward in the x is 0.2, and then this is the new y, so it gets fed in right there and right here in this particular problem. It's always going to get fed in right here, but depending on what this looks like, anything could kind of happen in here in this part. In this part, anything could happen. That's just what our differential equation said. And then you keep going and you keep going, and you can see that here's kind of what the picture turns out to be. I think this is, can we separate variables here? Not sure. I think this might be first order linear, right? If we go y prime, we add the y to the other side. Isn't that looking first order linear? That's what I'm thinking. But anyway, you solve that, you get the exact solution. Remember, you don't need the exact solution. Numerical techniques are for when you can't get an exact solution or for when getting one is really hard. So I hope that helped, and you should definitely watch those other videos too. I think a lot of your problems will have you compare some exact solution to a certain step size of Euler's method. So I hope this is fun, and if I have time, I'll also try to show you how to program this in Python or some other language. All right, see you next time.